Need vector search on a RAM budget? We'll compress embeddings with FAISS IVFPQ, tune nlist nprobe m/nbits, and measure recall K versus latency so results stay stable. You will walk away knowing how to compress a nearest neighbor index so it fits in far less memory while still returning useful nearest neighbors. I'm Professor Pi, teaching search and IR with simple Python. Vector search gets expensive in RAM when your embedding collection grows. FAISS IVFPQ exists because exact search over high-dimensional vectors uses a lot of memory and a lot of CPU. People reach for IVFPQ when they need to store millions of vectors on a single machine and still answer nearest neighbor queries quickly. Success here means smaller indexes, faster queries, and recall that stays acceptable. At a high level, IVFPQ mixes two ideas. First, it partitions the space into coarse buckets so each query looks in fewer places. Second, it compresses the vectors inside each bucket into compact codes so storage drops a lot. Think of it like sorting a library into shelves and then packing similar books into slim cases. We will build a simple baseline, train and evaluate IVFPQ, sweep a key search setting, measure the memory trade-off, and finally ship a tuned recipe you can reuse. This will make the concrete knobs feel familiar before we run anything. Now, we'll create a precise ground truth so we can compare approximate results. This snippet builds a FAISS flat L2 baseline and ground truth. It constructs a flat index that performs exact L2 nearest neighbor search, and then queries it to produce the reference neighbors we care about. The code loads the toy embedding collection, adds all vectors to the flat index, and runs a set of queries to record the true top neighbors. These ground truth results are what later recall measurements compare against. The important lines are the index construction, the add call that stores all vectors, and the search call that returns exact nearest neighbors. This gives a reliable baseline for timing and accuracy. Next, we will train and apply a compact IVFPQ index and compare quality. This snippet trains a FAISS IVFPQ index and measures recall at K. It first builds a coarse quantizer to assign vectors to buckets, then trains product quantization on residuals, and encodes the database into compact codes. The snippet adds the encoded vectors to the inverted file and runs the same query set used for the flat baseline. It computes recall at K, which measures how often the correct neighbor appears in the top K results, and reports query latency. The key knobs shown include the number of buckets for the coarse quantizer and the number of sub-quantizers used for compression. Changing those knobs trades memory for accuracy and slightly shifts query speed. Now, we will explore how the search time probe count affects recall. This snippet sweeps FAISS nprobe and selects the highest recall option. It runs the same queries for several values of the probe count, which is the number of coarse buckets the query inspects. Each run reports recall at K and latency, so you can see the trade-off curve. The sweep highlights that increasing the probe count improves recall, but costs more time per query. The selection logic picks the probe value that gives the best recall under a latency or memory constraint. This makes it easy to choose a practical nprobe for production. Next, we will estimate how much memory IVFPQ saves compared to exact storage. This snippet estimates IVFPQ memory versus flat index to show compression. It inspects the storage used by the flat index versus the compressed codes inside the IVFPQ index and reports a compression ratio. The calculation focuses on the dominant storage contributors such as the raw vectors in the flat case and the compact codebook plus codes in the IVFPQ case. This gives a clear quantitative sense of how many bytes per vector you can expect to save, and where the savings come from. Use this to justify deploying IVFPQ when RAM is limited. Finally, we will freeze a tuned IVFPQ configuration as a recipe you can copy. This snippet builds a tuned FAISS IVFPQ index as a baseline recipe. It picks the coarse bucket count and probe setting discovered in the sweep, retrains the index with your full dataset, and writes out the index object for serving. The snippet documents the chosen values so you can reproduce results. It also runs a quick verification query set to confirm recall at K and a timing check. This recipe acts as a stable starting point you can deploy or iterate from. Mapping this toy workflow to real systems is straightforward. Replace the small embedding set with your production embeddings. Train on a representative sample. Keep the same evaluation steps so recall and latency stay visible. Recap. What it is: FAISS IVFPQ is a two-stage approach that uses coarse partitioning plus product quantization to compress and speed up vector search. When to use it: when you need to store many embeddings on limited RAM and still serve nearest neighbor queries. One caveat: compression reduces accuracy, so measure recall at K and latency for your workload. Next step: tune nlist and nprobe together while watching recall at K and query time, and choose the lowest memory configuration that meets your recall target. If practical IR and clear recipes help you, subscribe and watch the rest of the IR videos.